Hello there, and welcome back to Worlds Beyond Seen. I'm so glad you found your way here tonight. Perhaps you're settling into bed or lying back in a quiet room, ready to let your mind drift through deep time and forgotten worlds. Wherever you are, whatever the hour, you're about to step into a moment of Earth's history that changed everything. A moment when the sky fell, the ice returned, and humanity's ancestors faced a catastrophe that would echo through millennia. Tonight, we're traveling to a time roughly 12,800 years ago, to an event that sits at the boundary between myth and memory, between geology and controversy. We're going to explore the Younger Dryas Impact hypothesis, a theory that suggests our planet was struck by fragments of a disintegrating comet, triggering one of the most dramatic climate reversals in recent geological history. It's a story of fire and ice, of extinction and survival, of a world transformed in an instant, and a climate that refused to warm for over 1,000 years. Before we begin this journey into deep time, I'd like to ask a small favour. If you enjoy these slow explorations through Earth's hidden past, please consider tapping the like button and subscribing to the channel. It helps more curious minds find their way here, and it lets me know that these quiet journeys into wonder are worth continuing. And if you're already subscribed, thank you, your support means everything. Now, settle in, let the tension drain from your shoulders, let your breathing slow to match the patient rhythm of geological time itself. Because we're about to witness something extraordinary. A planet on the verge of warming, suddenly plunged back into ice, a sky filled with fire, megafauna vanishing from the plains, and perhaps, just perhaps, the end of an ancient human culture that had begun to flourish. This isn't just a story about rocks falling from space. It's a story about resilience, about how life, including our own ancestors, adapted when the world changed almost overnight. So let's step back beyond written history, beyond pottery and agriculture, back to a time when mammoths still roamed and the great ice sheets were finally beginning their long retreat. Let's go to the Younger Dryas, the world before the impact. To understand what happened during the Younger Dryas, we first need to picture the Earth as it was just before a planet emerging from the grip of the last ice age, warming gradually, transforming from a frozen world into something greener, softer, more alive. This was the late Pleistocene, roughly 13,000 years ago. For tens of thousands of years, massive ice sheets had dominated the northern hemisphere. The Laurentide ice sheet sprawled across much of North America, a frozen wall of ice up to 2 miles thick in places, covering what is now Canada and extending deep into the modern United States. In Europe, the Fennoscandian ice sheet blanketed Scandinavia and parts of northern Europe. These weren't just patches of frozen ground, they were continental-scale glaciers, so massive they pressed the Earth's crust downward under their weight. But by 13,000 years ago, the planet was warming. The Bowling-Allerud interstadial, as scientists call it, was a period of relatively rapid climate improvement. Temperatures were rising across the globe. The great ice sheets, which had held the northern hemisphere in their frozen grip for millennia, were beginning to melt. Rivers of meltwater carved through the landscape, creating new lakes and flooding ancient valleys. Sea levels were rising as water locked in ice for thousands of years returned to the oceans. The world was greening. Forests were expanding northward from their Ice Age refuges. Grasslands spread across regions that had been barren tundra, and with the vegetation came life, vast herds of megafauna that defined this epoch. Picture the North American landscape, woolly mammoths moving in great herds across the steppe, their curved tusks sweeping through snow to reach the grasses beneath. Mastodons browsing on shrubs and trees at the edges of expanding forests. Giant ground sloths, some as large as elephants, lumbering through woodlands that were slowly reclaiming the land. Saber-toothed cats stalking prey in the lengthening shadows of twilight. Dire wolves hunting in packs across open plains. Enormous short-faced bears, the largest predators the continent had ever seen, ruling territories that spanned hundreds of miles. In Eurasia, the scene was similar. Woolly rhinoceroses, with their distinctive humped shoulders and thick coats. Steppe bison in countless numbers, cave lions, nearly twice the size of their modern relatives, and giant deer with antlers spanning 12 feet or more. In South America, creatures even stranger roamed: glyptodon, armored mammals the size of cars, and macrochenia, bizarre long-necked animals that looked like a cross between a camel and a tapir. These weren't just large animals, they were ecosystem engineers, shaping the landscape through their feeding, trampling, and movement. The mammoth steppe, that vast grassland ecosystem that stretched from Western Europe across Siberia to North America, was maintained in part by the grazing and browsing of these megaherbivores. Without them, the landscape would have looked entirely different, and in this world, humans were finding their place. The people living at the end of the Pleistocene were sophisticated hunter-gatherers. In North America, they're often associated with the Clovis culture, named after distinctive spear points first found near Clovis, New Mexico. These weren't primitive people struggling to survive, they were skilled craftsmen who created elegant, fluted projectile points with remarkable precision. They understood animal behavior, tracked game across vast distances, and developed strategies for hunting animals many times their size. Recent archaeological evidence suggests there may have been cultures in the Americas before Clovis, challenging the long-held belief that Clovis people were the first Americans. Pre-Clovis sites like Monteverde in Chile, dating to at least 14,500 years ago, indicate that humans had spread throughout the Americas earlier than once thought, adapting to diverse environments from Arctic tundra to tropical forests. In Europe and Asia, late Paleolithic cultures were similarly sophisticated. People created art, buried their dead with care and ceremony, built seasonal shelters, and passed down knowledge through oral traditions. They weren't just surviving, they were beginning to thrive as the world warmed and resources became more abundant. The climate during the Booling Alarerd was, by Ice Age standards, remarkably mild. Average temperatures in the northern hemisphere may have approached or even exceeded modern levels in some regions. Imagine standing on what would one day be the northern United States or southern Canada 13,000 years ago. The great ice sheet still loomed to the north, but it was in retreat, pulling back like a receding tide. Meltwater streams cascaded from its edge, feeding vast proglacial lakes, bodies of water held back by walls of ice or earth. One of these lakes, glacial Lake Agassiz, was enormous. At its peak, it covered an area larger than all of today's Great Lakes combined, stretching across parts of what are now Ontario, Manitoba, Saskatchewan, North Dakota, and Minnesota. It was held in place by the retreating Laurentide ice sheet to the north and by high ground to the south and east. The lake's volume fluctuated as ice barriers formed and broke, but it represented an enormous reservoir of fresh water just waiting for a pathway to the sea. The landscape was dynamic, constantly changing. Valleys carved by glacial meltwater were still being shaped. Newly exposed ground, scraped clean by the ice, was being colonized by hardy plants, first mosses and lichens, then grasses and small shrubs, and eventually trees as the soil developed and the climate continued to warm. This was a world in transition, a world caught between ice and warmth, a world where the future seemed bright and the long freeze appeared to be ending at last. But deep in space, something was approaching. The fragmentation of a comet. The solar system is not empty. Between the orbits of the planets, across the vast distances of interplanetary space, countless objects drift in silence, asteroids of iron and stone, comets of ice and dust, and debris from ancient collisions that have orbited the sun for billions of years. Most of these objects stay in their established paths, circling the sun in predictable orbits, posing no threat to Earth. But occasionally, gravitational interactions, the tug of Jupiter, the subtle influence of other planets, or a close encounter with another object can send something toward the inner solar system. Around 20,000 to 30,000 years ago, according to the Younger Dryas Impact hypothesis, a large comet entered the inner solar system. This wasn't a small chunk of ice. It may have been tens of kilometers across, a mountain of frozen water, carbon dioxide, methane, and dust that had formed in the outer reaches of the solar system billions of years earlier. As it approached the Sun, the comet's ices began to sublimate, turning directly from solid to gas under the Sun's heat. A glowing coma formed around the nucleus, a vast cloud of gas and dust millions of kilometers across. Behind it, the solar wind pushed material into a tail, a brilliant streamer that would have been visible from Earth, growing brighter night by night as the comet drew closer. But comets are fragile. Unlike solid asteroids of metal and stone, comets are loosely bound collections of ice and dust, often described as dirty snowballs. When they venture too close to the Sun, or when they experience strong tidal forces from passing near a large planet, they can break apart. This particular comet, researchers propose, fragmented. Perhaps it passed too close to the Sun, or perhaps the gravitational stress of passing near Jupiter or another massive planet pulled it apart. Whatever the cause, instead of one large object, there were now many a swarm of fragments, ranging from house-sized chunks to massive pieces kilometers across, all following roughly the same orbit but spread out along it like beads on a string. And that orbit intersected Earth's path. From the ground, the sight would have been spectacular and terrifying. Instead of a single bright comet crossing the night sky, there would have been a glowing stream, dozens, perhaps hundreds of bright objects, each with its own tail, all moving together across the heavens. To people with no understanding of celestial mechanics, it must have seemed like the sky itself was changing, like the stars were falling or the heavens were breaking apart. But the real terror was yet to come. Around 12,800 years ago, Earth passed through the densest part of this debris stream. What happened next is the subject of intense scientific debate, but the Younger Dryas Impact hypothesis proposes that multiple fragments, some possibly kilometers across, struck the planet. The impacts wouldn't have been like Hollywood movies, with a single massive asteroid creating a global catastrophe. Instead, this was an airburst event, or possibly multiple airbursts and impacts, where fragments exploded in the atmosphere or struck the surface across a wide area, primarily across North America but possibly in other regions as well. An airburst occurs when an incoming object, comet or asteroid, encounters Earth's atmosphere, and the tremendous stress of atmospheric entry causes it to fragment and explode before reaching the ground. The most famous modern example is the Tunguska event in Siberia in 1908, when an object estimated to be 50 to 60 meters across exploded about 5 to 10 kilometers above the ground, releasing energy equivalent to 10 to 15 megatons of TNT. The blast flattened trees across 2,000 square kilometers but left no crater. Now imagine not one Tunguska event, but dozens or hundreds occurring across a continent within hours or days. Fragments entering the atmosphere at tens of kilometers per second, heating to incandescence, the air around them compressed and superheated, then exploding with the force of multiple nuclear weapons, each blast creating a shockwave that radiated outward at supersonic speeds. The fireballs would have been visible for hundreds of kilometers. The thermal radiation, the intense heat from the explosions, would have been strong enough to ignite vegetation on the ground below, and the shock waves, when they reached the surface, would have flattened forests, killed animals, and created winds that fanned the flames. Some researchers propose that fragments also impacted the Laurentide ice sheet itself. When a high-velocity object strikes ice, the results are catastrophic. The impact energy melts vast quantities of ice almost instantaneously, creating enormous amounts of water vapor and liquid water. The shockwave radiates through the ice sheet, fracturing it, and the heat from the impact creates temporary pools of meltwater that can drain rapidly, sending floods of water and ice racing across the landscape. If multiple large fragments struck the ice sheet, the result would have been a pulse of meltwater unlike anything the planet had experienced in thousands of years. And that meltwater had to go somewhere, fire from the sky. Let's pause for a moment and try to imagine what it would have been like to witness this event. You're a human living 12,800 years ago, somewhere on the North American continent. Your people have followed the herds for generations, tracking mammoths and bison across the grasslands, fishing in clear streams, gathering plants and berries as the seasons change. The world has been warming. Each year, it seems, the ice to the north retreats a little further. The hunting has been good. Your children are growing strong. Then, one evening, someone points to the sky. There's something unusual, a bright streak moving among the stars. Over the following nights, it grows brighter. Then more appear. Within weeks, the night sky is filled with glowing objects, some so bright they cast shadows, all moving together in a slow procession across the heavens. The elders have no stories about such things. The shamans perform rituals, but the lights in the sky continue to grow, continue to approach. And then, one morning or evening, we don't know exactly when the sky catches fire. A brilliant light appears in the sky, brighter than the sun. Those looking directly at it are blinded instantly. The light grows, spreads, fills the entire sky with white-hot radiance. Animals flee in panic. Birds take flight in terror. And then the heat arrives, a wave of thermal radiation so intense that exposed skin blisters, that dry grass ignites, that the very air seems to burn. Seconds or minutes later, the shockwave arrives. A wall of compressed air moving faster than sound, carrying the sound of thunder multiplied 1,000-fold. Trees snap like twigs. Shelters are torn apart. Anyone standing in the open is knocked down, perhaps killed by flying debris or the shockwave itself. And this happens again and again. Across the continent, the sky erupts in fire, multiple airbursts, each one releasing energy equivalent to many nuclear weapons, create overlapping zones of destruction. In some areas, the blasts are far enough away that people see only the light and hear only distant thunder. In others, the devastation is total. Fires begin almost immediately. The thermal radiation from the airbursts ignites vegetation across vast areas. Strong winds generated by the explosions fan the flames. Within hours, wildfires are racing across the landscape, consuming forests and grasslands, driven by winds that seem to come from the burning sky itself. For animals, there is nowhere to run. Mammoths, masters of the Ice Age, find no refuge from fire. Their thick fur, adapted for cold, becomes a liability as embers rain down from the sky. Herds panic and scatter. Some flee into rivers or lakes, only to die from smoke inhalation or be overtaken by advancing flames. Ground sloths, too slow to escape, burn where they stand. Predators and prey alike perish in the inferno. And humans? Those close to the impacts likely died instantly from the thermal radiation, from the shockwave, or in the fires that followed. Those farther away faced a desperate struggle for survival. Communities were scattered, food supplies were destroyed. The landscape they knew was transformed into a charred wasteland. But the fire was only the beginning. The airbursts and impacts lofted enormous quantities of material into the atmosphere. Pulverized rock, vaporized ice, soot from the fires, and dust from the impacts mixed together in vast clouds that began spreading around the globe. This material, much of it fine enough to remain suspended in the atmosphere for months or years, began to block sunlight. Research into the Younger Dryas Impact hypothesis has identified several markers that might be evidence of these impacts. One of the most discussed is the presence of nanodiamonds in sediment layers dated to the onset of the Younger Dryas. Nanodiamonds are microscopic diamonds that can form under conditions of extreme heat and pressure conditions that occur during high-velocity impacts or airbursts. Similarly, researchers have reported finding magnetic microspherules, tiny spherical particles of melted rock or metal, high concentrations of platinum and iridium elements, rare on Earth's surface, but common in asteroids and comets, a layer of black matte material, rich in carbon and soot, and shocked quartz crystals with a distinctive pattern of fractures that form only under intense pressure. The interpretation of these markers is controversial. Some scientists argue they provide strong evidence for impacts. Others contend that these materials can form through other processes, wildfires, volcanic activity, or normal cosmic dust accumulation, and that their presence doesn't necessarily indicate a catastrophic impact event. But if the impact hypothesis is correct, These markers represent something profound, physical evidence of the day the sky fell, preserved in the sediment like fingerprints in dried mud, waiting 12,000 years to be discovered. The immediate aftermath. In the hours and days following the impacts, the Earth would have been a planet transformed. The immediate devastation was immense, but it was the secondary effects, the cascading consequences of the initial catastrophe that would reshape the climate and environment for more than 1,000 years. First, there were the fires. Wildfires ignited by the airbursts would have burned for weeks or months, consuming vast areas of forest and grassland. Research into similar events, such as the aftermath of the Chicxulub impact that ended the Cretaceous period 66 million years ago, suggests that impact-induced fires can spread across continental scales. The smoke from these fires would have been visible from space, vast plumes rising into the stratosphere and spreading on the wind. The smell of burning wood, burning grass, and burning flesh would have permeated the air for hundreds of kilometers downwind. At night, the horizon would have glowed orange and red as distant fires continued to burn. For survivors, both human and animal, finding clean air to breathe would have been a challenge. Smoke inhalation would have killed many who escaped the initial impacts. Those who survived would have suffered from respiratory problems, eye irritation, and the psychological trauma of watching their world burn. But worse than the fires was what they put into the atmosphere. Soot, the black carbon particles produced by incomplete combustion, is particularly effective at absorbing sunlight. When soot particles rise into the stratosphere, they can remain suspended for years, creating a layer that blocks incoming solar radiation and cools the planet. Models of nuclear winter, developed during the Cold War, showed how a global nuclear exchange could loft enough soot into the atmosphere to trigger dramatic cooling. Similar processes would have occurred after the Younger Dryas Impact. Even a relatively small amount of soot, millions of tons rather than billions, could trigger measurable cooling if distributed globally. And the distribution would have been global. Within weeks, atmospheric currents would have carried the soot and dust around the planet. The northern hemisphere would have been most affected, but the southern hemisphere wouldn't have been spared. Sunsets around the world would have turned deep red or purple as sunlight scattered through the particle-laden atmosphere. Days would have been dimmer, the sun visible only as a pale disk through the haze. As sunlight was blocked, temperatures began to drop. This wasn't a sudden freeze, not at first. The initial cooling would have been gradual, perhaps a few degrees over several weeks or months, but in a climate system that had been warming steadily for centuries, even a small drop in temperature could have significant consequences. One of the most important consequences involved the melting ice sheet. The Laurentide ice sheet, though in retreat, was still massive. It contained enough ice to raise global sea levels by many meters if it melted completely. And it was sitting atop North America like a frozen mountain range, with the melting ice creating vast lakes of fresh water at its edges and beneath it. If fragments of the comet struck the ice sheet, the impacts would have done more than create craters. The energy released would have melted enormous volumes of ice, creating instant rivers of meltwater. The shock waves would have fractured the ice, creating new pathways for water to flow, and the heating of the ice from below, if impacts penetrated deep enough, could have destabilized the entire structure. But there's another mechanism that may have been even more important: the sudden release of water from glacial lakes. Remember Lake Agassiz, that enormous body of fresh water held back by ice and earth? As the ice sheet melted and retreated, the level of this lake fluctuated. At times, it drained southward through the Mississippi River system into the Gulf of Mexico. At other times, ice barriers blocked this outlet, and the water had nowhere to go. The impacts and their associated earthquakes caused by the shock waves radiating through the Earth's crust may have been enough to breach these ice barriers. Or the sudden addition of meltwater from impacts on the ice sheet may have caused the lake to overflow its natural barriers. What happened next would have been catastrophic. Imagine a wall of water, a freshwater tsunami rushing across the landscape, millions or billions of gallons per second, carrying ice blocks the size of houses, sediment, and debris, flowing faster than a person could run. Valleys that had been carved by glaciers over thousands of years would have been reshaped in hours or days as this mega flood scoured the land. There's geological evidence for such floods. The channeled scablands of Washington state, for instance, were carved by repeated catastrophic floods during the last ice age, when glacial Lake Missoula, a smaller cousin of Lake Agassiz, repeatedly filled and burst. The landscape there shows clear signs of massive water flow, giant ripples in the bedrock, dry waterfalls hundreds of feet high, and enormous boulders transported dozens of kilometers from their source. If Lake Agassiz experienced a similar catastrophic drainage, the water would have had to go somewhere. The most likely path, given the topography at the time, would have been through the Great Lakes region and out through the Strait, Lawrence River Valley into the North Atlantic Ocean, and that's where the real climate catastrophe began. The ocean conveyor stops. The North Atlantic Ocean is not just water, it's a vast, three-dimensional river of currents, a system of flowing water that helps regulate the Earth's climate. And at the heart of this system is what scientists call the Atlantic Meridional Overturning Circulation, or AMOC. Here's how it works. Warm, salty water flows north from the tropics, carried by the Gulf Stream and its extension, the North Atlantic Current. As this water moves north, it loses heat to the atmosphere, warming northern Europe and keeping the climate there much milder than it would otherwise be at those latitudes. The cooling water becomes denser. When it reaches the seas around Greenland and the Norwegian Sea, it's cold and salty enough to sink a process called deep water formation. This sinking water then flows south as a deep, cold current, eventually circling Antarctica and spreading into the Indian and Pacific Oceans. The surface flow northward and the deep flow southward create a kind of conveyor belt, moving heat from the equator toward the poles and playing a crucial role in regulating global climate. But this system has a vulnerability. It depends on the density difference between the warm surface water and the cold deep water. And one way to reduce that density difference is to add fresh water to the North Atlantic. Fresh water is less dense than salt water. When large amounts of fresh water enter the ocean, they can form a layer on top of the salty water, preventing the salty water from sinking. If enough fresh water is added, the entire conveyor belt can slow down or shut down entirely. This is where the catastrophic drainage of Lake Agassiz comes in. If billions or trillions of gallons of fresh water suddenly poured into the North Atlantic through the St. Lawrence River, it would have created a massive lens of low salinity water across the ocean's surface. This fresh water, being less dense than the underlying salty water, would have prevented deep water formation. The sinking of cold, salty water that drives the entire conveyor belt would have stopped. Without the Atlantic Meridional Overturning Circulation, the Gulf Stream would have weakened or even halted its northward flow of warm water. Northern Europe, Greenland, and eastern North America, which had been warmed by this ocean current, would have suddenly lost their primary heat source. The result would have been rapid cooling, particularly in winter. Temperatures in the North Atlantic region could have dropped by 10-15 degrees Celsius, 27 degrees Fahrenheit, within a matter of years or even months. Summer temperatures would have fallen as well, though not as dramatically. This scenario, a shutdown of the Atlantic Meridional Overturning Circulation triggered by freshwater influx, is well established in paleoclimatology. Evidence from ocean sediment cores shows that it has happened multiple times during the last ice age, causing abrupt climate shifts. The question is whether it happened at the start of the Younger Dryas, and if so, what triggered the freshwater pulse. The traditional explanation is that the freshwater came from the gradual drainage of Lake Agassiz as the ice sheet retreated naturally. But the Younger Dryas Impact hypothesis proposes a more dramatic trigger, that comet fragments striking the ice sheet, or the impact's shock waves and associated heating, caused a sudden catastrophic release of meltwater, overwhelming the North Atlantic with fresh water in a matter of days or weeks rather than years. The cooling that followed would have been swift and severe. The return of the ice. The Earth, which had been warming for centuries, suddenly reversed course. The Younger Dryas period began, named after an Arctic alpine wildflower, Dryas octopetala, whose pollen suddenly becomes abundant in European sediment cores, from this time a sign that cold-loving plants were spreading south again as the climate deteriorated. The onset was remarkably abrupt. Ice core records from Greenland, which provide year-by-year climate data going back tens of thousands of years, show that the temperature drop at the start of the Younger Dryas occurred over the course of just a few years to a few decades. One of the most detailed records from the Greenland Ice Sheet Project, GISP, to ice core, suggests the transition happened in less than 20 years, an eye blink in geological terms. For people living through it, this would have been terrifying. Imagine being a child when the impacts occurred, and a young adult when the climate turned cold. The world your parents described, the warming world, the expanding forests, the abundant game would seem like a distant memory or a story from a more generous time. Glaciers that had been in retreat for centuries suddenly stopped, stabilized, and in many areas began advancing again. Moraines, ridges of rock and sediment pushed ahead of glaciers from this period are found throughout the northern hemisphere, marking the positions where glaciers halted their retreat and pushed back. The Younger Dryas climate wasn't quite as cold as the peak of the last ice age, but it was close. Average temperatures in the northern hemisphere dropped by perhaps 5 to 10 degrees Celsius, 9-18 degrees Fahrenheit, compared to the warmer period just before. In some regions, particularly near the North Atlantic, the cooling was even more severe. The impact on ecosystems was profound. Forests that had been expanding northward retreated. Trees died as winters became harsher and growing seasons shortened. Grasslands shrank as well, in some areas replaced by tundra, a sparse, cold landscape of mosses, lichens, and low-growing shrubs that could tolerate the harsh conditions. For animals, this represented another crisis on top of the immediate devastation from the impacts. The megafauna of the Pleistocene were already stressed. Now they faced a rapidly changing climate that made food scarce and survival more difficult. Many species didn't make it. The Great Extinction, the end of the Pleistocene epoch, saw one of the most dramatic extinction events of the last 100,000 years. Across North America, South America, Europe, Asia, and Australia, dozens of species of large mammals vanished. This extinction was selective. It primarily affected megafauna animals, weighing more than 44 kilograms, about 100 pounds, while smaller mammals survived. In North America, the losses were staggering. By the time the Younger Dryas ended, around 11,600 years ago, the continent had lost roughly 70% of its large mammal species. Woolly mammoths, mastodons, giant ground sloths, saber-toothed cats, dire wolves, American lions, American cheetahs, short-faced bears, giant beavers, the size of bears, and many others all disappeared. The Columbian mammoth, which stood up to 4 meters tall and was one of the largest elephants ever to exist, vanished entirely from a continent it had roamed for hundreds of thousands of years. South America's losses were even more severe, with approximately 80% of large mammal genera going extinct. The giant ground sloths that had been a defining feature of the American landscape for millions of years were gone. So were the elephant-sized glyptodon with their armored shells, the bizarre macrauchenia, and the massive predators that had hunted them. In Eurasia, the extinctions were less severe, but still significant. Woolly mammoths survived in Siberia for thousands of years after their North American cousins vanished, with dwarf populations persisting on remote Arctic islands until as recently as 4,000 years ago. But the woolly rhinoceros, the cave bear, the giant deer, and many other species disappeared during or shortly after the Younger Dryas. What caused this wave of extinctions? The debate has raged for decades, and there's no single answer. Two main hypotheses have competed for dominance: climate change and human hunting. The climate change hypothesis points to the rapid environmental shifts at the end of the Pleistocene. As the climate warmed after the last glacial maximum, then cooled again during the Younger Dryas, then warmed once more, ecosystems were repeatedly disrupted. Species adapted to Ice Age conditions found their habitats shrinking, Those adapted to warmer conditions faced the return of cold. Some species, particularly megafauna with slow reproduction rates and long generation times, couldn't adapt quickly enough. The human hunting hypothesis, often called the overkill hypothesis, suggests that the arrival and spread of human hunters, armed with effective weapons and hunting strategies, led to the rapid extinction of naive megafauna that had never encountered humans before. Proponents point to the correlation between human arrival and extinction in various regions. Australia's megafauna largely vanished soon after humans arrived about 50,000 years ago. North America's extinctions roughly coincide with the spread of the Clovis culture, and remote islands saw extinctions when humans finally reached them, even in historical times. The Younger Dryas Impact hypothesis adds another layer to this debate. If there were indeed multiple impacts or airbursts at the onset of the Younger Dryas, the immediate effects, the fires, the explosions, the destruction of habitat would have been catastrophic for megafauna. Animals already stressed by hunting pressure from humans would have been pushed beyond their limits. Consider a population of mammoths in North America. By 13,000 years ago, they had already been hunted by humans for hundreds or thousands of years. Their populations may have been declining. Then came the impacts, fires destroying vegetation, shockwaves killing animals directly, and a sudden cooling that made food even scarcer. For a species with a long gestation period, 22 months, and slow population growth, recovery from such a catastrophe would be nearly impossible. Moreover, the loss of any species can trigger cascading effects through an ecosystem. The extinction of large herbivores would have affected the predators that depended on them. It would have changed vegetation patterns, as forests and grasslands were no longer being shaped by the feeding and trampling of mega-herbivores, and it would have disrupted nutrient cycling, as the enormous amount of dung produced by herds of mammoths and other large animals had played a role in fertilizing the landscape. The debate continues, but most researchers now accept that the megafaunal extinctions were likely caused by a combination of factors: climate change, human hunting, and possibly habitat destruction from impacts or other causes. The Younger Dryas wasn't the sole cause, but it may have been the final stress that pushed vulnerable populations over the edge. For humans living through this time, the loss of megafauna would have been devastating in its own right. Mammoths and other large animals weren't just a food source, they were raw materials. Their bones were used for tools and shelter. Their hides provided clothing and containers. Their ivory was carved into art and implements. As these animals vanished, human societies had to adapt, and many did, in remarkable ways. Human survival and adaptation. The period from the Younger Dryas impacts through the end of the Younger Dryas itself, roughly 12,800 to 11,600 years ago, was one of the most challenging times for human societies in the Northern Hemisphere. But it was also a time of remarkable innovation and adaptation. In North America, the archaeological record shows significant changes. The Clovis culture, once widespread across the continent, disappears from the record around the time of the Younger Dryas onset. What happened to the Clovis people is a matter of ongoing research and debate. Some archaeologists argue that the culture simply evolved, with Clovis technology giving way to other styles of projectile points. The Folsom point, for instance, which was smaller and more finely crafted, perhaps adapted for hunting different prey as the megafauna vanished. Others suggest that population disruptions, possibly related to the climatic changes or the impact events, caused a breakdown of the widespread Clovis culture into more regionally distinct groups. What's clear is that humans survived. They didn't vanish from the archaeological record, they adapted. Sites from the Younger Dryas period show evidence of diversified subsistence strategies. Rather than specializing in hunting large game, people began exploiting a wider range of resources: smaller mammals, birds, fish, shellfish, and plant foods. In Europe and the Near East, the Younger Dryas also coincided with significant cultural changes. The Natufian culture in the Levant, modern-day Israel, Palestine, Jordan, Lebanon, and Syria had begun to settle in permanent or semi-permanent villages and to harvest wild grains intensively. When the Younger Dryas brought cooler, drier conditions to the region, these wild grain stands may have shrunk. This environmental pressure, some researchers argue, may have been one of the factors that pushed Natufian people toward true agriculture, toward deliberately planting and cultivating crops, rather than just harvesting wild stands. By the end of the Younger Dryas, the first domesticated grains appear in the archaeological record. Wheat and barley, the foundations of Near Eastern agriculture and later of civilizations, were being deliberately cultivated. This is one of the great paradoxes of the Younger Dryas. A period of environmental catastrophe and climate deterioration may have helped spur one of humanity's most important innovations, agriculture. Faced with scarcity, humans experimented with new ways of producing food, and some of those experiments worked well enough that they spread, eventually transforming human society from mobile hunter-gatherers to settled farmers. In other regions, different adaptations emerged. In coastal areas, people increasingly exploited marine resources. Shell middens, ancient garbage dumps composed primarily of discarded shells from this period, show intensive use of shellfish, fish, and marine mammals. The ocean, less affected by the land-based climate changes, provided a stable food source, but survival came at a cost. Skeletal remains from the Younger Dryas period sometimes show signs of nutritional stress, periods of inadequate diet, particularly in childhood. Populations may have declined in some regions, and culturally, the disruptions likely led to the loss of knowledge, the fragmentation of social networks, and the stress of living in a world that was no longer as generous as it had been. For over 1,000 years, humans persisted in this colder world. They told stories, created art, buried their dead, and maintained the knowledge that allowed them to survive in harsh conditions. And they waited, though they didn't know they were waiting, for the climate to shift again. The geological evidence. So, how do we know all this? How can scientists reconstruct climate and environmental conditions from 12,800 years ago with enough precision to talk about events happening over years or even seasons? The answer lies in multiple lines of geological and archaeological evidence, each one a different window into the past. Ice cores are among the most valuable. When snow falls in places like Greenland or Antarctica, it accumulates in layers year after year, forming ice sheets thousands of meters thick. Each layer preserves a snapshot of atmospheric conditions when it fell, the temperature, the composition of the atmosphere, even dust and volcanic ash that was in the air. By drilling deep into these ice sheets and extracting long cylinders of ice, scientists can literally read Earth's climate history. The ice cores from Greenland have been particularly valuable for understanding the Younger Dryas. They show the abrupt cooling at the onset, the sustained cold period that followed, and the equally abrupt warming at the end. But ice cores also preserve other information. Trapped air bubbles contain samples of the ancient atmosphere, allowing scientists to measure greenhouse gas concentrations. Dust layers tell us about volcanic eruptions or periods of increased aridity. And isotopes in the ice itself, different forms of hydrogen and oxygen, act as a thermometer, recording temperature changes with remarkable precision. Lake sediment cores provide a different kind of record. Lakes, particularly those that have existed for thousands or millions of years without drying up, accumulate layers of sediment on their bottoms, mud, organic matter, pollen grains, and microscopic organisms. By drilling cores from the lake bottom, scientists can examine these layers and reconstruct past environments. Pollen grains are particularly useful. Different plant species produce distinctively shaped pollen, and this pollen settles into lake sediments, where it can be preserved for thousands of years. By counting and identifying pollen grains in different layers, researchers can determine which plants were growing around the lake at different times. A shift from tree pollen to grass and shrub pollen might indicate a change from forest to tundra. The appearance of cold-loving species like Dryas octopetala signals cooling. Ocean sediment cores work similarly, but on an even longer timescale. The deep ocean floor accumulates sediment very slowly, often just a few centimeters per 1,000 years, but some of these cores span millions of years of Earth history. Microscopic organisms called foraminifera, whose shells accumulate in ocean sediments, can be analysed for their isotopic composition, which reveals information about ocean temperature and ice volume. One particularly powerful technique looks at the ratio of two oxygen isotopes, oxygen 1,6 and oxygen 1,8, in foraminifera shells. This ratio changes depending on how much ice is locked up on land, because water molecules with lighter oxygen 1,6 evaporate more easily and get preferentially incorporated into ice sheets, leaving the ocean enriched in heavier oxygen 1,8. Then there's direct dating, radiocarbon dating, which measures the decay of carbon 14 inches organic materials, allows scientists to determine the age of bones, charcoal, wood, and other carbon-containing materials up to about 50,000 years old. By dating materials from different archaeological sites and geological layers, researchers can construct a timeline of events. And there's the impact evidence itself, the controversial markers that have sparked so much debate. Nanodiamonds, those microscopic diamond crystals, have been reported in sediment layers dated to the onset of the Younger Dryas at multiple sites across North America and Europe. If confirmed, and if their formation requires high pressure, high temperature events like impacts, they would be powerful evidence for the impact hypothesis. Platinum and iridium anomalies, spikes in the concentration of these elements, have also been reported in Younger Dryas boundary layers. These elements are rare in Earth's crust, but more common in asteroids and comets, so their presence in elevated concentrations could indicate extraterrestrial material. A black mat, a dark carbon-rich layer, found at many sites across North America and dated to the Younger Dryas onset, could represent soot and charcoal from massive wildfires. Its widespread distribution suggests fires on a continental scale. Meltwater pulses and sea level changes provide another line of evidence. If massive amounts of ice melted suddenly at the start of the Younger Dryas, we should see evidence of this in the geological record. And we do. There are indications of a meltwater pulse around this time, though its exact timing and magnitude are still being refined. Finally, there's the evidence from the scablands, those landscapes carved by megafloods. The channeled scablands of Washington state show clear evidence of catastrophic flooding. Similar features have been identified in other regions. Dating these flood events is challenging, but some may coincide with the Younger Dryas onset. Taken together, these different lines of evidence paint a picture of the Younger Dryas: an abrupt climate reversal, widespread environmental change, possible impact markers, evidence of massive fires and floods, and a wave of extinctions. But the exact cause, whether it was an impact, a meltwater pulse from gradual ice sheet collapse, or some other mechanism, remains debated. The controversy and debate. Science thrives on controversy, on competing hypotheses tested against evidence, on debates that force researchers to refine their ideas and look more carefully at the data. And few topics in recent paleoclimatology have been as controversial as the Younger Dryas impact hypothesis. When the hypothesis was first proposed in a major paper in 2007 by Richard Firestone, Alan West, and colleagues, it generated immediate attention and immediate skepticism. The idea was bold, that a cosmic impact had triggered one of the most significant climate events of the last 20,000 years, had caused mass extinctions, and had possibly even destroyed early human civilizations. The response from the scientific community was mixed. Some researchers found the evidence compelling and began looking for additional support. Others were highly critical, questioning both the evidence presented and the interpretation of that evidence. One major area of debate centers on the impact markers themselves. When other researchers attempted to replicate the findings looking for nanodiamonds, platinum anomalies, and other indicators in sediments from the same time period, the results were inconsistent. Some studies found the markers, others didn't. Some researchers questioned whether the nanodiamonds were actually nanodiamonds or could have formed through other processes. Others pointed out that platinum anomalies could result from volcanic activity or changes in sedimentation rates rather than impacts. The black mat layer, initially interpreted as evidence of widespread fires, has also been re-examined. Some researchers argue that black mats are common features in North American sediments, and don't necessarily indicate continent-wide burning. They can form in wetland environments where organic matter accumulates and is preserved. The fact that black mats are found at many sites dated to the Younger Dryas onset might simply reflect the climate change of the period, which would have altered drainage and created more wetland environments. Another challenge to the impact hypothesis comes from the lack of a clear crater. If one or more large fragments struck the Earth, where did they hit? Some proponents have suggested that impacts on the Laurentide ice sheet wouldn't leave obvious craters because the ice would have melted away. Others have proposed that airbursts, rather than surface impacts, were responsible for most of the effects. And airbursts don't create craters. But critics point out that even airbursts should leave some markers, shocked minerals in the soil, for instance, or clear evidence of extreme heating. And multiple large airbursts over a continent should leave abundant evidence. The fact that such evidence is controversial and inconsistently reported raises questions. The mechanism linking impacts to climate change has also been questioned. Would impacts on the ice sheet really have been enough to trigger a catastrophic meltwater pulse? Some models suggest that even multiple impacts wouldn't melt enough ice to shut down the Atlantic circulation. Others argue that the climate system was already on the verge of a cold reversal, and that impacts, if they occurred, might have been a trigger, but not the fundamental cause. Then there's the extinction question. If impacts caused the megafaunal extinctions, why did different regions see extinctions at different times? Australia's megafauna had already been gone for tens of thousands of years by the Younger Dryas. Madagascar's megafauna survived until humans arrived much later, and some species, like the woolly mammoth in Siberia, survived the Younger Dryas and persisted for thousands of years afterward. Despite these criticisms, research into the hypothesis continues. New papers are published regularly, some supporting the impact hypothesis, others challenging it. The debate has pushed researchers to look more carefully at the Younger Dryas boundary, to develop better dating techniques, to search for additional evidence, and to refine their understanding of how impacts would affect the Earth system. In 2018, a study reported finding a large impact structure beneath the Hiawatha Glacier in northwest Greenland. This crater, about 31 kilometers across, was initially suggested as a possible candidate for a Younger Dryas impact. However, subsequent dating has been controversial, with some studies suggesting the crater is much older, perhaps millions of years, while others argue it could be younger. The question remains open. This is how science works. A bold hypothesis is proposed, evidence is gathered, other researchers attempt to replicate the findings or find contradictory evidence. Debates happen at conferences, in journals, and through new research. Over time, either the hypothesis gains support and becomes accepted, it's modified to fit new evidence, or it's abandoned in favour of better explanations. For the Younger Dryas impact hypothesis, we're still in the middle of that process. The hypothesis has forced scientists to reconsider the onset of the Younger Dryas, to look for evidence of impacts that might have been missed, and to think about how cosmic events can influence Earth's climate. Whether it's ultimately proven correct, modified, or disproven, it has already contributed to our understanding by pushing the boundaries of what we investigate. The end of the Younger Dryas and the birth of civilization. The Younger Dryas didn't last forever. Around 11,700 years ago, about 1,200 years after it began, the climate shifted again, and this time, the shift was even more abrupt than the onset. Ice core records from Greenland show that temperatures rose dramatically by perhaps 10 degrees Celsius, 18 degrees Fahrenheit, or more in some regions over the course of just a few years to a few decades. One particularly detailed analysis of the GISP-2 ice core suggests that most of the warming occurred over just 3 years. 3 years to end a millennium of cold. The mechanism of this warming is still being studied, but it likely involved the Atlantic circulation restarting. As the fresh water that had shut down the oceanic conveyor belt was gradually mixed into the ocean or diluted by salty water flowing in from other regions, the density contrast that drives deep water formation was re-established. Warm water began flowing north again. and the climate of the North Atlantic region warmed rapidly. The end of the Younger Dryas marks the boundary between the Pleistocene and Holocene epochs. The Holocene, our current geological epoch, began with this warming, and the climate has remained relatively stable and warm ever since. This stability has been crucial for the development of human civilization. As the climate warmed, glaciers retreated more rapidly than ever. The great ice sheets that had dominated the northern hemisphere for tens of thousands of years finally began their terminal collapse. Sea levels rose as meltwater returned to the oceans. Coastlines shifted, drowning the land bridges that had connected continents and islands. Forests expanded northward, reclaiming lands that had been tundra. Grasslands spread. Rivers carved new channels and filled valleys. The landscape transformed once more. For humans, this was an opportunity. With a stable, warm climate and abundant resources, populations could grow. Settlements became more permanent, and in several regions around the world, almost simultaneously in geological terms, humans began to experiment more seriously with agriculture. In the Fertile Crescent of the Near East, wheat and barley that had been cultivated on a small scale during the Younger Dryas were now planted more systematically. People began to settle in year-round villages, to store grain, to domesticate animals. The Neolithic Revolution, the transition from hunting and gathering to agriculture, was underway. In China, rice cultivation began. In Mesoamerica, maize was domesticated. In the Andes, potatoes and quinoa. In West Africa, millet and sorghum. In different regions, using different plants and animals, human societies independently developed agriculture and began the long transformation from mobile hunter-gatherers to settled farmers. With agriculture came surplus. With surplus came specialization. Some people could focus on tasks other than food production, making pottery, weaving cloth, crafting tools, practicing religious rituals, governing, organizing defense. Villages grew into towns. Towns grew into cities. Writing was invented to keep track of stores and taxes. Mathematics developed. Trade networks expanded. And within a few thousand years, the first civilizations, Sumer in Mesopotamia, Egypt along the Nile, the Indus Valley civilization, the early Chinese dynasties emerged and began recording their own histories. It's a remarkable thought. All of recorded human history, all of civilization as we know it, has occurred within the Holocene, within this warm, stable period that began when the Younger Dryas ended. The cities, the empires, the art and literature and science and philosophy, all of it has unfolded in the last 11,700 years. And what came before? Ice and cold and the struggle to survive in a world that was harsh and constantly changing. The people who lived through the Younger Dryas didn't build pyramids or write epics, but they passed down knowledge that allowed their descendants to flourish when the climate finally stabilized. Some researchers have speculated controversially that memories of the Younger Dryas impacts and climate change might have been preserved in myths and legends. The flood myths found in cultures around the world, the stories of fire from the sky, the tales of a lost golden age before catastrophe struck. Could these be distorted memories of real events from the end of the Pleistocene? It's impossible to know. Oral traditions can preserve remarkably accurate information over long periods, but they also evolve, incorporate new elements, and blend fact with fiction. Still, it's intriguing to consider that when ancient peoples spoke of a time when giants megafauna walked the earth, when fire rained from the sky, when the world was drowned in flood, they might have been, in some distant way, remembering the Younger Dryas. What the Younger Dryas teaches us. As we drift toward the end of this journey, it's worth reflecting on what the Younger Dryas, whether or not it was triggered by cosmic impacts, teaches us about our planet and our place in its history. First, it reminds us that Earth's climate is not stable. We often think of nature as being in balance, but the geological record shows that climate can change rapidly and dramatically. The Younger Dryas was just one of many abrupt climate shifts in Earth's history. Understanding these past changes helps us understand the climate system's sensitivity and the potential for future changes. Second, it shows us that cosmic events can and do affect Earth. We live in a solar system filled with debris, asteroids, comets, dust, and rocky fragments. Most of this material is harmless, but occasionally something large enough to cause damage crosses our path. The Younger Dryas Impact hypothesis, whether fully supported or not, has refocused attention on impact hazards and the importance of monitoring near-Earth objects. Third, it demonstrates the resilience and adaptability of life, including human life. The Younger Dryas was a catastrophic period, yet humans survived and even innovated during it. The same is true for many other species. Life is remarkably persistent, able to adapt to changing conditions, to find new food sources, to survive in harsh environments. But fourth, and perhaps most sobering, it shows us that extinction is real and permanent. The mammoths, the giant ground sloths, the saber-toothed cats they didn't survive. Once gone, they're gone forever, except as fossils and DNA fragments. The Younger Dryas extinctions remind us that species, even dominant ones that have existed for millions of years, can vanish within a few thousand years or less when conditions change too rapidly or catastrophe strikes. Finally, the Younger Dryas and the debates surrounding it demonstrate the power and limitations of science. We can reconstruct past climates with remarkable precision, can date events to within decades or even years, can read the composition of the ancient atmosphere from bubbles trapped in ice, and can identify elements in sediments that hint at extraterrestrial origins. And yet, we still debate what happened 12,800 years ago. We still argue about evidence, about mechanisms, about causes and effects. Science is a process, not a collection of fixed truths. It's a way of asking questions, testing ideas, and refining our understanding. And sometimes the most interesting questions are the ones we can't yet definitively answer. Closing thoughts. A planet shaped by catastrophe. As you lie here, perhaps on the edge of sleep, consider this. The planet beneath you has been shaped by catastrophe, not once, but many times. The very ground you rest on was formed by volcanic eruptions, shifted by tectonic collisions, carved by glaciers, and weathered by wind and water. The Younger Dryas, whether triggered by comet fragments or by other causes, was one moment in this long history of change. A moment when the sky might have burned, when ice returned, when species vanished, and when the ancestors of every human alive today faced one of their greatest challenges. They survived, they adapted, they told stories around their fires, passed down knowledge to their children, and slowly, over generations, built the foundation for everything that came after. You are here because they endured. The mammoths didn't make it, the giant sloths didn't make it, but humans did, and in the warm stability of the Holocene that followed, humans flourished, built civilizations, developed agriculture and writing and mathematics, explored the world, looked up at the stars, and eventually figured out how to read the ancient record of ice and sediment and bone. We've learned to look backward through time, to see the climate shifts and impact events and extinctions of the past, and in doing so, we've learned that our time here is both precious and precarious. The climate that has been so stable for the last 11,000 years, the climate that allowed civilization to develop, is not guaranteed to last forever. Changes can be abrupt, catastrophes can happen, but we've also learned that we are not helpless. We can study the past, understand the mechanisms that drive change, and perhaps, if we're wise enough, prepare for the future. The Younger Dryas is a window into that past, a reminder of how quickly a world can change, and a testament to the resilience of life. Whether it was triggered by fire from the sky or by the slower processes of melting ice and shifting currents, it shaped the world we inherited. And now, as you drift towards sleep, let your mind wander back through those 12,000 years. Picture the ice retreating, the forests expanding, the first seeds being planted in careful rows, the first villages rising from the plains. See the continents taking their modern shapes as the seas rose. Watch as humans spread across the globe, adapting to every environment from Arctic tundra to tropical rainforest. All of this unfolded in the aftermath of the Younger Dryas, in the space created when the ice finally released its grip and the climate stabilized into the warm interglacial we still enjoy. Rest now in this moment of stability, knowing that beneath the peace of the present lie layers of catastrophe and change, extinction and survival, endings and beginnings stretching back through deep time. The Earth remembers it all, written in ice and stone and bone, and we, through science and curiosity and careful study, are learning to read that ancient script, to understand the story of our planet and our place in it. Sleep well. Dream of mammoths walking across endless plains, of ice sheets glowing under northern lights, of comets streaking across the sky, of forests returning after the long freeze. Dream of a world that was, and a world that might be again, and the strange, beautiful, resilient story of life on a planet that has weathered countless storms. The Younger Dryas came and went. The ice returned and retreated. Species vanished and new ones rose. And through it all, somewhere in the chaos and change, a small group of humans kept the fire burning, kept the knowledge alive, and passed it forward to us. May we do the same. Good night.